So we are going to talk about decomposition of multi-channel data. And I'm going to focus in this talk on PCA. We have a number of things that you can decompose multi-channel data. And since, let's say, the last decades, multi-channel data in neuroscience has become much more important than it was several years ago. Because several years ago, a single channel was really an expensive business, because an amplifier to record an EEG or to record a single unit was something that a lab could maybe afford, but certainly not 10 or 100 of them. Nowadays, that's very different. Also, if you think about all the imaging technique that people use, basically making movies, that every pixel is basically a signal that moves across time. So you get very impressive data sets, all multi-channel. And then, of course, you have also cases where you have multiple sources that basically affect one channel. And I think a number of you, I know that Lisa has done this, but a number of you have looked at multi-unit spike activity in a single channel and tried to decompose that. That's another way of looking at channels where you need to do some decomposition. We are going to look again at PCA, and at the most important thing you need to know in order to understand PCA is a little bit of linear algebra. So I'm going to get that out of the way first. I'm going to give you some reminders. The most important for PCA is this one. It's eigenvectors and eigenvalues. Now, eigen is a German word, and you can, in this context, you can basically translate it as characteristic. And if you have a matrix, let's say C, and a vector U, then this is the important equation that you need to recall. And if you don't know about this, maybe you should, at some point in time, review this for yourself. What happens here is you multiply a matrix with a vector, and basically what that matrix does to the vector is that it rescales it by a value of lambda. So this is a value, this is a matrix, and these are the same vectors. Now this thing is called the eigenvalue, and this thing is called the eigenvector. And as you will see with PCA, that's basically what it boils down to. You find the eigenvalues and the eigenvectors of the covariance matrix, as you will understand in a little bit. Another important thing to recall is transpose. And basically, if you have the transpose of a matrix, let's say that you have elements ij, then basically that means that the transpose is simply changing the columns and the rows. And as you can see, you use this little character t. So if you transpose C, you basically indicate that quite often with a t. And then the other thing is something that will come up too, is the symmetric matrix. And a symmetric matrix is when this is true. So basically, if the element at ij is equal to the element at ji. And as you can see from the line above, that means that in this case, the transpose of a matrix will be equal to the matrix itself. And that's something we will use too. Another one that comes up in a little bit is the term diagonal matrix. And a diagonal matrix is a matrix where the elements ij are 0 if I is not j. So that means that only values in the diagonal of the matrix are potentially non-zero. All the other ones are zero. And that also plays an important role with principal component analysis. Another one related to that, the trace of a matrix. That's the sum of the diagonal elements. Yet another one, we're closing to the end, or that's about all we're going to need, is the inverse matrix. As you probably know, not every matrix has an inverse, but many of them do, and we are dealing with the case where matrices do have it. And it's usually indicated as a -1, so the inverse of C is C minus 1, and if you look at this product, you will get the identity matrix, and the identity matrix is a diagonal matrix with all ones in the middle, and we will use that as well. So if you're not familiar with any of that, you will see I'm going to use it. If you kind of want to see proof of that, go to a linear algebra textbook and review it. None of it is very complex. Now for PCA, we will focus on covariance matrix C. And as a matter of fact, I'm using the covariance matrix. You could also have a variant of the PCA where you normalize the covariance matrix and then it's the correlation matrix. But in a way, the procedure is not different. Now, as we will see, covariance matrix C is a symmetric matrix, and that's important. And its values are real. That's important too, because since it's a symmetric matrix with real values, we also have real eigenvalues. As we will see. And this is really critical in PCA. The eigenvectors are orthogonal. And again, this is kind of give you a little bit of a preview of what we will see and what we will do. And this is a little bit a preview of all the different things we are going to utilize to derive the whole PCA procedure. What's the idea of PCA? Basically, again, I already alluded to it a little bit in the beginning. The idea is that you are decomposing some signal, either a multi-channel signal or a signal where you have multiple effects of different sources. And you're basically looking at a mixed signal and you're trying to unmix it. And I have a little figure that I'm going to project, and actually you have that figure in the stuff that I emailed to you. So if you haven't received that, you will receive it, so don't bother writing this up or trying to get used to the lights again. It will be a little moment for this thing to warm up. And if you can see it there in the corner, feel free to kind of move your chair. So this is the idea in a little diagram. We have a setup, we have a number of sources. Here we have 3 sources, x1, x2 and x3. And we basically arrange these sources in a capital X. And we have in this case also, to keep it simple and tractable, we have 3 sensors, y1, y2, y3, and they're arranged in capital Y. And what we are now going to assume, which is kind of common in neuroscience, if you think about, let's say, an earthquake, and you want to look at the source, then you have to think about how much time it takes of these tremblings of the earthquake to get to your sensor. Of course, in neuroscience, everything moves at the speed of light, and the electrical signals and the magnetic signals. And the distances are very small, so basically in neuroscience you really don't worry too much about propagation speed. Everything is almost instantaneous. But the thing that does really affect the propagation of signals to a sensor is the distance between the source and the sensor. So in this particular case, you see, for instance, that this source has a very strong effect on this sensor. This source has a very strong effect on this sensor, but this source has a little bit less of an effect on this sensor because it's farther away. And here it's symbolized by the width of the arrow. And of course this source has also some effect on this sensor, but that's even less. And so now suppose for the case of this example, that we would know what the attenuation is, and then we say, well, the attenuation here is 0.8, this is 0.6, and this is 0.2. And if I know all these attenuations from every source to every sensor, I can basically write up a little equation, isn't it? I can, for instance, for x1, I could say, well, x1, if I multiply that by 0.8, 0.6 times, what did I say, 0.2? Yeah, 0.2 times x3. That's basically going to be my signal in y1. And similarly, I could write an equation for y2. And similarly, I could write an equation for y3, isn't it? I mean, since I know all the attenuations and all the distances, everything is very tractable, pleasant, and I know everything. And of course, I can then, if I have 3 equations, one for y1, one for y2, one for y3, I can put that in a mixing equation, which means that y is just a times x. And a is nothing else than all these coefficients, 0.8, 0.6, 0.2. So I have now my sources, I have my mixing matrix, I multiply the two, and I get what my sensors are measuring. Now the thing is that, of course, as a neuroscientist, you don't know what your sources are, but you do know what your sensors are measuring. So in a way, this is kind of my forward problem. I know what my sources are, I happen to know what the mixing rules are, and I can compute what the sensors are doing. The neuroscientist says, well, yeah, that's nice, but I know this one, and I want to know that one. And in some cases where you have a really tractable problem like here, you can say, well, in that case, if A is an invertible matrix, which it happened to be here, I can basically recompute my sources by computing this product, A minus 1 times Y. And I know Y because I measured it. I know A minus 1 because I know A. And now I can find my sources. And in the handout that you will get, hopefully, when the email is collaborating, you will see that when you do these numbers and when you do these computations in MATLAB, you basically get your answer back. If you then have a certain source signal, and here and there you have a couple of different signals, and these are your measurements that you compute with this equation. If you then basically recompute the source signals from your measurements, you will get a perfect answer. Maybe you have some rounding errors, but in principle it's all tractable. Now the bad news is, because you think, well, that's easy, so we can go home now. The bad thing is that it's not always that easy, because very often you have you don't know where your sources are. So you don't know what A is. You don't know how many sources there are. And usually, certainly if you record an EEG from a whole brain, you can be darn sure that you will have more sources than that you have electrodes. And so the idea that you have 3 sources and 3 electrodes is also basically something that doesn't always work that well. In that case, you have to do something to kind of deal with this. And in principle, you have then called the blind source separation, or BSS. And PCA, principal component analysis, and also ICA, independent component analysis, are examples of such a blind source separation. And the motivation is thus, you want to do something that looks like this, but you can't in a number of cases, and then you use these techniques. Is that clear? If it is, then we're going to kind of now focus on PCA, and depending on how the timing goes, I may say a few words about ICA, but otherwise I may actually do an ICA lecture in my own course in the spring later. But now I want to focus on the PCA because it's more fundamental and it's also a little bit easier. So, PCA. What I like to do is a little example. Where we have a bunch of measurements. And then we'll just go through the steps what you would do if you did a principal component analysis. So let's say that we have 4 measurements. S1, S2, S3, and S4. And let's say that I arrange that in a matrix. So this is the numerical example. And let's say that every measurement, let's say that this is my measurement S1. Every measurement has three elements. And this is my second measurement. And this is my fourth measurement. Well, the first thing you want to do, which is what I already kind of mentioned a little while ago, is that we want to go to the covariance matrix. And in order to get to the covariance matrix, we want to demean this observation. That's actually something you do a lot in signal analysis. You're not very interested in the absolute values. You want to see what the fluctuations are. And in that case, what you do is you compute the mean value. That means that I add all these things up and divide them by 4, isn't it? So if I didn't make any mistakes, in my notes it says that this is the mean value. Let's see, yeah, that's correct. At least that part is correct. So now we get the mean data by subtracting the mean from every observation. And let's call that the mean matrix B. So you can see here I have here my demeaned observation B1 up to my demeaned observation B4. And if you basically look at across the measurements, because these are different measurements, the different columns, basically as long as I stay within a row, I would look at variance. How much is the variability of this one? How much is the variability of that one? And how much is the variability of that part of the observation? And the other thing that we are interested in often is how are things correlated, or how do they co-vary? So how is the relationship between this row and that row, and this row and that row? That's the covariance, or if you normalize it, it's the correlation. Now that's kind of the whole idea. And if you now want to look at variance and covariance, you can actually very easily compute that from this vector. But before I do that, I want to show you what it looks like in a 3D plot. Should have left this thing on. Where we plot these observations and these observations. And this is a little MATLAB script that I will also give you. So graphically, the first step that you do is here are your here is your origin 0, 0, 0, and basically here are the 4 observations. So these are S1, S2, S3, and S4. So these observations here are plotted in 3D there, relative to the origin. And this, by the way, this little dot in the middle is M. And so the first step towards a PCA is that you basically redraw your axes, and that you plot everything relative to that mean value. That's the first thing that you want to do. So the first thing of PCA is translation of the axes. And that's easily accomplished because you just subtract the mean, isn't it? But that's step 1. Now the next step is going to be a little more complicated, because now we need to kind of start to compute the covariance matrix, and that is what we are going to do now. I'm going to try to obscure this thing instead of turning it on and off all the time. That's my low-tech remote control. So now in order to get from here to the covariance matrix, I compute C. And C is nothing else than the normalized product of B with its transpose. And that kind of determines how they co-vary or how they vary. And then you normalize in this case by 1 over n minus 1. You may also do 1 over n. As far as I'm concerned, that's not a big deal. If you do that, you will get a covariance matrix that looks like this. And again, this will be in the handout, so don't worry about the details. This is the covariance matrix. Question, or a bunch of questions actually. In this covariance matrix, where is the variance? Anyone, not Lisa?
The diagonal?
Yeah, it's the diagonal. So this is basically the variance between 1 and 1, 2 and 2, and 3 and 3. That's correct. And so where is the covariance? That's everywhere else, correct? So this is covariance between 1 and 3. And this is covariance between 2 and 3. So the covariance matrix contains the variance. The variance is on the trace, on the diagonal. If you want to know what is the total variance, you compute the trace, and then you basically have the total variance. And everything else is covariance. What is something, what else is kind of noteworthy here in this matrix? I already told you that in the beginning it would be symmetric, and you see indeed it is symmetric. So why is it symmetric? Are you surprised? Yeah, yeah. Correctly, you're not surprised because the covariance between 1 and 2 is the same as 2 and 1. And so these things are the same. 1 and 3 and 1 are the same too. And so basically you're not surprised that that thing is symmetric. You could also say, well, if it is symmetric, then this should be true, isn't it? Because a symmetric matrix, the transpose of a symmetric matrix, is itself again, isn't it? That's one of the rules that we had listed all the way in the beginning. And you can easily see that that is true as well, because if you kind of expand this, you get BTT, BT, because you have to change the order now, if I take the parentheses away. And the question is this easy, is this the same to BT? And the answer is absolutely, because the transpose of the transpose is basically itself again. And so you can also apply a simple linear algebra rule to demonstrate that this is a symmetric matrix. So now we go to the next goal of the PCA. The goal of the PCA is not only to kind of translate the axes and use that to get a better sight on how your observations are arranged, but the next goal of PCA is to make all covariance vanish. So what we want is to translate and now rotate the axes in such a way that we are going to deal with a covariance matrix that has only values in the diagonal and where all the other values are 0. And another way of saying that, of course, is that you want to have you want to remove correlation. Because again, covariance and correlation are very related. Correlation is the normalized version of that. So how are we going to do that? And now we're going to take a step back, and then we're going to come back to our numerical example. We're going to first kind of see what the strategy of how to do that is. So we're going to transform our normalized or demeaned, not normalized, demeaned observations B into a matrix V. And we're going to accordingly basically transform our covariance matrix C in covariance matrix sigma. And sigma has to be diagonal. So in our case, what we want, because we have 3 observations, is we want to have something like this, isn't it? Only some non-zero values in the diagonal and 0 elsewhere. That's what we want. And then we have decorrelated our stuff. Now, what I'm going to do is I'm going to show you by a number of assumptions what we could do, and then after the fact I'm going to show you that it actually works. So now let's assume we have matrix U with orthogonal vectors U1, U2, and U3. In a way that we satisfy the following. Basically C times U. C is again the covariance matrix. Would then be CU1, CU2, CU3, isn't it? And U1, U2, U3 are column vectors in this case. So I could, if you want to, I could put little arrows above that, but we do that all the time here now that we have observation vectors that we arrange in matrices. So. And the other thing that we want is that mu sigma, which is again U1, U2, U3, times sigma, which we had said was lambda 1, lambda 2, lambda 3, and 0 elsewhere, would now become lambda 1 U1 lambda 2 U2 and lambda 3 U3. Now we're gonna rearrange things a little bit. I assume this is all pretty straightforward for you, isn't it? If it isn't, let me know. So we are now going to take this equation and rearrange it a little bit so that we get an expression for C. And here we assume, though, that U has an inverse, as you can see. and also now we get a somewhat interesting result here, because if you look at this one, actually the left part is this thing, the right part is this thing. So that means that if I can equate these two, that I can say that basically all these elements are can be equated. So that means that C U1 is, in this case, is equal to lambda 1 U1. And C U2 is lambda 2 U2, and etc. Why is this interesting? Well, this is interesting because this exactly shows that we have here the typical equation for the eigenvector and eigenvalue. So that's kind of what I mentioned earlier. That is kind of something that actually is the basis for this whole PCA analysis. And you cannot clearly see yet where we are going with this, but you will see in a minute. The other thing you have to kind of keep track of is this equation. I'm going to come back to this one in a little bit too. But now at least we have already established that in this case we are dealing with an eigenvalue eigenvector situation. And the same one you can write down for U2 and U3. And that's I'm not going to write that down, but that's obvious. I make this equal, and that equal. So now the question is, because you could look a little bit glassy, and most of you do, how are we going to use this, and how are we going to accomplish this? And now I will kind of slowly get back to the example, almost there. We're going to set B is equal to UV, and B again was the mean data, and V was the vector that we want to get. Kind of keep track of this. This is what we want. So this is what we're going to say. If that's the case, and there is an inverse of U, we can also write this one. And what's kind of interesting here is that you can say that U minus 1 is equal to the transpose of U. And the reason is that U is an orthogonal matrix. That's the reason that you may say U minus 1 equals UT. As a matter of fact, if you have a hard time, do a couple of examples and you will see it's correct. So we now are going to compute sigma. And sigma is the covariance matrix of V, isn't it? Okay. So basically that following the same equation we did before, we now have to normalize V times Vt to compute the covariance matrix for V. And since I know that V is minus UB, and minus UB is the same as UTB, I can substitute that in here. And now I will kind of slowly get back to the example, almost there. We going to set B is equal to UV, and B again was the vector that we want to get. So this is what we want. So this is what we're going to say. If that's the case, and there is an inverse of U, we can also write this one. And And now I can again get rid of the parentheses. And keep in mind that if you have a transpose of an expression in parentheses, you have to change the order. So then this thing is going to read as this is UTT, but again the transpose of a transpose is itself again. So now I've gotten rid of the parentheses. And if I write this a little bit, if I rearrange this a little bit, I get this, isn't it? This is just a number, a scalar value, so I can move that. And as you can see, this was our covariance matrix C, by definition. Anything you note now? Yeah, sigma equals this thing. Huh? So we did it, see? Because this is what we wanted. I told you I would come back to this. This is what we wanted to do. And so this is the way we can do that. And so what we need to do is we need to be able to find the basically the eigenvectors and the eigenvalues of C. And once we have the eigenvectors and the eigenvalues of C, we basically can use that to basically rescale the whole thing. And that actually, since it's an orthogonal matrix, you probably also recall from linear algebra, that means that we are going to rotate our axes. So the first part was really the simplest part. That was demeaning the data, which meant translating the axis to the mean value. And then the next step that we want to do is to get rid of all the correlations. And we can do that by computing the eigenvectors and the eigenvalues, but especially the eigenvectors of the covariance matrix of the mean data of C. And then we can use that to translate our axes. And if we do that, we end up with our normalized or renormalized or rotated observations V. And the interesting thing is that the covariance matrix of V is sigma. And the property of that one is that it has only diagonal elements. So now we have basically, by doing this little trick of rotating the axes, we have changed our observations relative to a set of axes where all correlations have disappeared. Let me show you what that means in our example. So recall that what we did first was we had our original observations relative to whatever axes we used for our measurements. Then we said, well, we are not interested in that. We want to kind of do it relative to the mean. So we translated it. And we computed the covariance matrix relative to the translated values. And then the next thing we are going to do now is we are going to use this covariance matrix to compute the eigenvectors. And then here are the eigenvectors, and they basically create also 3 axes. They are rotated now. They are orthogonal, so they are nicely like axes are supposed to be, orthogonal relative to each other. And as you can see, this is the first principal component, this is the second one, and that is the third one. So they're orthogonal, and if we now basically measure the same measurements that we had before relative to these axes, they are decorrelated. They don't have any more correlations. That's the idea of PCA in a nutshell. So then the next thing comes, of course, now okay, we have done this, and this is kind of neat, isn't it? We now decorrelated our stuff, but now the question becomes, what do these axes represent? Any suggestions? Yeah, very good. So that's a good start. Now let's kind of see if we can do one step further. Because you're right, we arranged them according to the amount of change. Well, one trick you could do, because there's really no hard science in making an idea of what these axes represent. One thing you could do is say, well, the most extreme point along these axes is this point and that point. So you could see, for instance, oh, but these are all the ones with blue hair, and these are all the ones with green hair. That must be it. It must be hair color or something like that. So that's kind of what you normally try to do, since it's the most variance you have. You look at your extremes and you see if that can give you a clue of what this axis really means in this case. So that's kind of how you do this. Let's kind of now, unless there are questions, look at some applications. And these applications are also MATLAB scripts that you will get, so just watch them. Any questions before we move on? Let's look at an application here that some of you may know. And I'll just show you a very theoretical example of a spike sorting routine. Let's kind of use PCA to see if we can spike sort. And the way that I always recommend that you test your algorithms is you come up first with some synthetic example. Because if your algorithm doesn't work on a more or less ideal synthetic example, you can forget it will ever work on real data. So that's always a good idea to try that first. So let's say that we have 2 types of waveforms of ideal spike shapes. This is one of them, the black one, and this, the triphasic one, is the other one. And now let's kind of see if we put this in a signal situation where we add noise and DC and stuff like that, if we can now use PCA to really distinguish these 2 spike shapes. You can see I added some DC to this one and noise, and I added some other level of DC to this one and some noise. And I say DC, that's kind of an engineering term, I mean offset. DC is direct current, it's more an engineering term. So the first thing we do when we do PCA is that we demean the data. So that's basically the first step. And here you see the superimposed and the mean data. So we have here, and now they nicely fluctuate around 0. And I can now use that to compute my covariance matrix of this observation. And then the next step will be to look at the PCA. And what I'm showing you here are PC1, PC2, and PC3. And you can see they do a great job. You can easily distinguish the two. But there is something else that is also apparent in this plot. Let me ask you this: which components contribute most to the separation? 1 and 2, yeah. And 1 and 2 and 3 basically doesn't do anything, is it? Because if you would be looking across this axis, you would have a hard time really distinguishing the two. So 1 and 2 really do a good job. 3 really doesn't add much, and I'll show you here even the ones for 3 and 4. You see, if I just showed you the stuff plotted against components 3 and 4, yeah, you can see them because I color-coded them red and black, but you would not be able to distinguish them. And so in this case, it's clear. I have two cases. I have two components that can nicely separate them. So I could, for the same token, and actually if you want to do that, you get the MATLAB routine. You can basically plot it just against PC2 and PC1, and you will see two nice separated dots. And that's all you need to separate them. Of course, this is a very synthetic and ideal example where we have really similar waveforms that do not change over time. It's all stationary. It's all nice. The noise is there, but it's an additive noise. It's random noise that behaves well. So in all reality, and I would actually suggest you try this on some real data at some point in time. Maybe in one of your rotations, you will see that things are not as ideal as in this example. But again, if you have an algorithm, it's best to try it on an ideal example first, because you want to make sure, in principle, it works. In reality, of course, spike waves change a little bit over time, and noise is not always nicely Gaussian, and on and on and on. You may also have a record with 10 or 20 or 30 neurons contributing to it. And there may be overlap in waveform properties, so it may not always be as easy as two nicely separated waveforms. But you can see in a relatively simple case this really works quite well, and you don't need anything fancy to distinguish the two waveforms. A last example I wanted to give you is to show you that PCA can also be used in cases where you want to separate signal and noise. And of course it's not particularly designed for that, but if your signal is kind of a major component and the noise is relatively small in amplitude, it sometimes works. And I use here an image from Lena. Lena is a pinup, and I only show you the decent part of Lena here. But Lena is a picture here that's often used for signal analysis on images. And I deteriorated Lena with some noise. And I computed the principal components of Lena. And here you see the components. And here you see the cumulative effect of the components. And I'll start it again. I'll show you basically the effect of component 1 up to component 30. And when I run it again, you will see that the first components basically contain much more of the signal, whereas if you come higher up and higher up and higher up, then components start to really contain more of the noisy characteristic of that image. So now it's done. It has ran up to 1 up to 30. So look at it again. I will run it one more time. This is the original. This is the one that I spoiled completely by adding noise. These are the individual components, and these are the cumulative effects. So you will see this image will get better and better and better. And then if I keep adding components, it will get noisier and noisier and noisier again. So there we go again. I hope. Yep. So now you see it's component 4. And you can already see Lena appear a little bit. See now up to component 10. You can also see here that the blocks basically get smaller and smaller. So basically it gets noisier. And now slowly you will see that the image starts to get noisier. Now we get up in these components. So of course this only works if this may not work in a situation where you have low frequency noise or where you have high amplitude low frequency noise. But if you have an image that's relatively decent and you have some relatively high frequency noise that can be distinguished in the higher components, then this technique may actually work. That's the PCA component, and since I have a few minutes, I'm going to say a few things about ICA. And I think now I can turn this thing off. Yeah.
So in that example, how many components can you have?
Oh, that's a good question. How many components can you have? Look back at our example. We had 4 observations, but every observation had 3 elements, and our covariance matrix was basically 3 by 3. And that basically determines how many eigenvectors you can have. So it depends on how you arrange your measurements, but basically the number of elements that you have in the observation determines how many components you can have. And in this case I showed you up to 30, but I could have shown you a lot more, of course, because this is an image of probably 256 by 256 or 512 by 512.
So it'd be the number of pixels.
Yeah. Any other questions? Good. So what we did with PCA is basically we decorrelated the data. PCA is decorrelation. ICA goes a little step further because now we want to have the component statistically independent. Now, a number of you may say, well, isn't that the same thing? If data is uncorrelated, is it also statistically independent? Any suggestions? No, I disagree. Now, PCA basically, if you do for the data that you have recorded, there is no correlation left. No. So what is the difference between statistically independent and decorrelated? And the answer, the real answer is that depends whether it's the same or not. If you have data that is normally distributed, then decorrelation means that you're also statistically independent. But if your data is not normally distributed, then decorrelation may not mean that it's also statistically independent. It's not the same thing in that case. Because in, let's say that if you have a non-normal distribution with higher moments, such as skewness and kurtosis and basically non-normal things, that means that what the statisticians call the higher moments in that distribution are basically important. And that means if you have a decorrelation, you only made that the second moment, the correlation is 0. But the higher moments may still be kind of dependent. So this is a stronger procedure than this one, provided that your data is not normal distributed. If your data is normal distributed, it basically comes down to the same thing. Now the nice thing is, of course, that in many data, certainly in compound data, that is the result of a number of processes. Due to the central limit theorem, things are usually normally distributed. But in neuroscience, nonetheless, you deal often with not normally distributed data. And in that case, it is basically maybe a better idea to use ICA. But depending on how my series goes in the spring, I may come back to that. And otherwise, the handout that you get is part of a chapter of this book. Otherwise, I can refer you to that. So. And I think here we will stop.